In this lesson, we're going to go over complex numbers and specifically arithmetic with complex numbers. To start with, what is the square root of -1? If you type this into a calculator, it's going to say error or something similar to that, meaning it doesn't work. The reason for this is if you call this x, and then let's say square both sides to get rid of that square root, this changes the equation to this. -1 is equal to x squared. And if you take a real number and square it, it's either positive or zero, can't be negative. This is just our way of saying you can't put a negative number under a square root and get a real number back. But what you can do is call it something else. You can say, well, all right, it's not a real number, but maybe I'll define it to be something else. And we're going to call that thing I. The square root of -1 is called I because it is an imaginary number. So it's our way of saying it's not a real number. This allows you to define something called a complex number. A complex number is any number of the form a plus b times I, where a and b are real numbers, and here I, it's our way of defining or relabeling the square root of -1. Another way to say this is if you square both sides, if you square I, it's equal to -1. Because if you square both sides of this expression, well, on the left you get I squared, and squaring a square root cancels the square root. With this definition, you are allowed to now talk about complex numbers and how to graph them in something called the complex plane. So instead of thinking of this as the x and the y axis, we call this axis the real axis. So I'll say this is the real axis. And we call this axis the imaginary axis. So I'll put imaginary up here. So if you want to graph a number like, let's say, 2 plus 3i, this is the real number, and the 3 is the one that's attached to the imaginary number. You can't combine them because they're not like terms, but if you want to graph this thing, you can say, okay, we'll go 2 in the real direction and 3 in the imaginary, and this is the point 2 plus 3i right here. If you want to graph, let's say, -4 minus I or minus 1i, you would go backwards 4 on the real axis and down 1 in the imaginary to give us this value here. This is 4 minus 1i. If you want to graph, let's say, -3i, well, here you're saying there's 0 for the real part. So you don't go left or right on the real axis, but you go down 3 to go to -3i. So this is just the same thing as saying -3i. So a complex number has a real component and an imaginary component. And when you think of it this way, you can graph these numbers in the complex plane where it has a real and imaginary axis. So like I said, in this lesson, we're going to focus on arithmetic with complex numbers. But it turns out, even though they're called complex or imaginary, you can do some pretty interesting things with them. So I just put one thing down here for you if you'd like to look into it. But this is called the Mandelbrot Set, which is this image. This thing exists in the complex plane, and it can be generated by a computer. So there is a real and imaginary axis. It's just not put in with the image. But basically, this thing is a fractal. So you can zoom in on it forever, and it's infinitely complete. So I'd suggest looking or searching Mandelbrot Set Zoom on YouTube. There's some really interesting things. And my favorite one will show up if you do this search right here. So you should check that out. It's pretty interesting. But like I said, we're going to focus on just arithmetic with imaginary and complex numbers. Here in example 1, I'd like to add and subtract the following complex numbers. Let's start with this one here. Here we have 1 plus 2i, and that's being added to 4 plus 7i. How can we add these two complex numbers together? The way we can do this is, well, we don't really need the parentheses, so I'm going to rewrite this as 1 plus 2i plus 4 plus 7i. And we're going to treat the real parts as like terms, because you can add 1 and 4, and the imaginary parts as like terms as well. So you can take 2i and add it to 7i. If we add these together, 1 plus 4 is 5, and then 2i plus 7i is 9i. So this is the sum of the two complex numbers. Basically, you combine like terms, add the real parts to get 5, add the imaginary parts to get 9i. So that was addition. What about subtraction? What we'll do here is get rid of the parentheses, but to do so, you have to distribute the negative to both terms over here. So I have to multiply that negative to the 4 and the negative 8i. If we do that, the first complex number doesn't change. It's just negative 3 plus 2i. But if I distribute in the negative, I get negative 4 plus 8i. The next step is to combine like terms. Here I have a negative 3 and a negative 4. And I also have a positive 2i and a positive 8i. If we combine the like terms, negative 3 and negative 4 is negative 7, and 2i plus 8i is 10i. And that is how you would combine those. So addition and subtraction, relatively straightforward. Here, multiplying, something that you have to be a little bit more careful with. So to start with, I'm just going to put down the definition of I, in that it is the square root of negative 1. Or equivalently, if you square both sides of this equation, if you square I, it's equal to negative 1. Using that, let's multiply these two values together, 3i and then 6 plus 10i. The way you do that is by, well, you'd have to distribute the 3i into the parentheses. So this becomes 3i times 6 plus 3i times 10i. If I look at this first piece, everything's being multiplied together. I know 3 times 6 is 18. And I have I there as well, and that's it. 3 times I times 6 is 18i. Now over here, I have 3 times I times 10 times I. Well, I can multiply the 3 and the 10, that's 30. And then you can multiply I times I. So you have I times I. But I times I is I squared because you're multiplying the same thing together. So I'll put this as, well, it's 18i plus 30i squared. And because I squared is negative 1, I'm going to replace this with something more simple. So I'm going to put a negative 1 here with parentheses. That is, we have 18i plus 30 times negative 1. Now 30 times negative 1 is just negative 30, so I have 18i minus 30. And that's it. You really can't take this any further. It might be nice to write it so the real part is first and the imaginary part is second, but everything's multiplied out. There's no like terms that can be combined, and that's the answer. Now, what if we have something like this? 1 plus I and then 2 minus 3i. Here wasn't so bad because you could just distribute the 3i. But down here, you have to be a little bit more careful because you have to use FOIL. That is, 1 has to be multiplied to both terms. But then I has to be multiplied to both terms as well. We got to distribute. Now, when we do that, when I first multiply in the 1 times 2 is 2. And 1 times minus 3i, that's minus 3i. So that was multiplying in the 1. Next, I have to multiply in the I, so it's I times 2. I'm going to write that as 2i. And then I times this 3i, we'll get minus 3. And I know I times I is I squared, so I'm just going to put I squared. This came from I times the I squared. But like we said before, I squared is negative 1, so I'm going to replace this with negative 1. So we get 2 minus 3i plus 2i minus 3 times negative 1. Now, a minus and a minus here all gives me a positive 3, so I'm going to place that as 2 minus 3i plus 2i, and then we get plus 3. I now have some like terms that can be combined. 2 added to 3 is 5. And 3i plus 2i is minus I. I can't simplify that any further, and that's the final answer. All right, let's try a couple more. Here we have 5 plus I times 5 minus I. So again, I'm going to distribute to solve this. 5 times 5, and then I'm going to multiply 5 times minus I. And then I'm going to multiply in the I. When I do that, when I multiply in the 5 times 5 is 25, and 5 times minus I is minus 5i. Okay, next, I times 5 is positive 5i, and we have, well, it's got to be negative. I times I is I squared. And if you want, you could just put a negative 1 there. But just be careful that it's a negative 1 times this negative. So I'll put in that extra step. But this is 25 minus 5i plus 5i. Then we have minus this negative 1, which changes it to a plus 1. And when we combine like terms, well, the 1 and the 25 is 26. Minus 5i and positive 5i, those two things completely cancel. In fact, if you want, just for emphasis, you could put, well, there is no imaginary part, but simplified, it's just the number 26, which is a real number. It's possible that when you multiply two complex numbers together, you get a real number back. Now, it's no surprise this happened here, kind of like looking back at it, because the middle terms were equal and opposite. That will happen anytime that you take a complex number and the only thing you do is switch it from either positive to negative or negative to positive. So if it's like almost the same number, but the only difference is positive and negative, your answer will be a real number. So this is like a nice observation to make. It could save you some time. I just know the answer is going to be 5 times 5, which is 25. And then I times I, which changes to a positive 1, which is why the answer is 26. Now what about this? 5 plus I squared. If you want to simplify this thing, it might be nice to write it as 5 plus I times 5 plus I. Written this way, it's easier to see that, okay, we'll distribute again. 5 goes to 5, and then, well, 5 goes to I, and then also multiply in the I to both terms. I'm not expecting this to be a real number because, well, here, they're exactly the same. They don't differ in sign at all. 5 times 5 is 25. 5 times I is 5i. I times 5 is also 5i. And then I times I is I squared. This is really 25 plus 10i. And then I squared is negative 1, and it just remains negative 1. If I combine like terms, 25 minus 1 is 24. And nothing combines. I only have 10i. And this is my answer. Just something to be careful with. If you see a squared here, it doesn't mean just square the 5 and the I. I'd suggest rewriting it and then distributing out each term. In this last example, let's simplify this expression. So here we have some negatives under a square root, which means we're not going to have real numbers for our answer, but that's okay. We can use imaginary numbers. To start with, the square root of negative 4, I think of that as the square root of 4 times negative 1. And likewise, for the square root of negative 25, I'm thinking of that as the square root of 25 times negative 1. The reason for this is you can break it up into two separate square roots. The square root of 4 times the square root of negative 1. Likewise, the square root of 25 times the square root of negative 1. Square root of 4 is 2, and the square root of negative 1 is what we're calling our imaginary number I. Likewise, for the square root of 25, that's 5, and the square root of negative 1 is I. We can combine this to say we have 7i, and that is the simplified answer. Once you see how this works, it might be fine to go directly from this step to this one. When I look at this, I see a 4, and it makes me think under the square root, it'll just give me a 2. And the fact that I see this negative here means I'll just include this I at the end to indicate that it's imaginary. Same thing for this. I really saw the 25 and I thought, oh, well, that's going to go to 5. Here I have a negative, so I know I'll put this I at the end. So you don't have to show this work when going from here to here. There's nothing wrong with it, but this is really just to justify why we get to this answer here.